Hi, Nancy.
Hey, Shane.
So today we have a little bit of a different format, I guess, or whatever. But we're beaming in from New Mexico.
Yeah.
One of our colleagues, Larry O'Hanlon, no
relation
to me. Hi, Larry.
Hey, Shane. Yeah, no relation. I have an O. You have no O.
Yeah.
But
So,
you
Larry,
you have O envy. I've heard. You told me that once.
Oh, I do. Yeah. No,
Yeah,
that's a whole other
it'll be
episode.
cool. Yeah, right. That's a whole other story. But so Larry, New Mexico. So you told us a fun fact about New Mexico. Can you?
Yeah. Well, many people. I mean, New Mexico only has about 2 million people in the whole state, so it's not a very big state. I mean, people-wise, and a lot of people. It's surprising how many people don't even realize it's a state. There's a very popular magazine called New Mexico Magazine, and at the end of the magazine, they have this feature called "One of the 50 is Missing," and people write in their stories about how people don't, things they run across where people think they have to bring pesos here or need a passport.
Oh, so they really think it's literally like New, Mexico?
Like it's a part of Mexico. Okay.
Yeah,
Interesting.
people think there's like Texas and Arizona, and they just kind of forget that there's New Mexico in between. So yeah,
Oh, that's funny.
it's a weird state in that way, right?
I mean, I guess like Nancy and I both live in Virginia, but we can definitely at least relate because I mean the district is not like DC is not a state, but it's like the flip side. People always think the DC is a state, and when you tell them like District of Columbia is not a state, they're like, "What? What do you mean?" Like, yeah. Think about that for a second.
Yeah,
like, voting rights, representation. Yeah, maybe opinions on DC and New Mexico could swap.
yeah, it's kind of backwards, isn't it? Right.
Welcome to the American Geophysical Union's podcast about the scientists and the methods behind the science. These are the stories you won't read in the manuscript or hear in a lecture. I'm Shane Hanlon.
And I'm Nancy Bompey.
And this is Third Pod from the Sun.
So Larry, hi. So being down there in New Mexico, you have the opportunity to talk to scientists that we up here in DC don't necessarily get to talk to every day.
Yeah, we have a couple of national labs. So I went up to Los Alamos National Lab. It's about an hour from where I am, and talked to a couple of the scientists there about work they're doing related to the Mars rovers, the one that's there, the one that's coming, as well as about life on Mars and how you search for life on Mars by looking at stuff on Earth.
I'm Nina Lanza, and I'm a scientist at Los Alamos National Laboratory.
Chris Yeager, also at Los Alamos National Laboratory. I'm a microbiologist.
Okay, and this is Larry O'Hanlon with AGU. So we're here to talk about a few things, but primarily I think it's about looking for life on Mars, right?
Yeah,
Okay.
we're looking. We'll let you know when we find it. Spoiler alert, we haven't found it yet.
Now, but this has been a search that's been going on for a long time. I mean, I remember I think I was a kid when the Viking landers.
Nav is green for touchdown. ACS is green, 1.5 degrees per second max.
I'm old enough to remember that.
Touchdown, we have touchdown.
And there was a lot of excitement about, they thought they'd found something, but then they thought, well, maybe not. And Can you kind of talk about a little bit about the background of searching for life on Mars to kind of get us into this?
Sure. Well, Mars has really captured the human imagination just because it looks so Earth-like.
For hundreds of years, the planet Mars has been the subject of heated controversy among scientists and imaginative speculation by science fiction writers.
Even, before we ever landed anything there, we had telescopes that could show us these features on the surface. And in fact, some folks have misinterpreted some of those features to be, grand canals and maybe cities.
Obviously, the work of intelligent Martians, the simplicity and symmetry cannot possibly
I think
be
these
the work
are canals, massive engineering works which provide water for irrigation and commerce.
It will be possible with larger telescopes to see cities on Mars.
Which turned out it's not actually the case, but this is, it has been very in our imaginations, it's a place where life could have existed. But we're actually not that far off, because right now, even the way that Mars is now, which is pretty cold and pretty dry, there are life forms on Earth that would happily thrive there, right? And so it has all the ingredients for life. So now the question is it there? Was it there? How would we know? And so we have sent some landers and rovers to the surface of Mars. And you mentioned Viking. Viking was very exciting.
It's probably the most sophisticated spacecraft ever designed for any purpose. It's going to Mars, it's going to land on Mars, and it's going to orbit around Mars at the same time.
It was the first time we'd touched the surface of Mars. Unfortunately, we landed in some places that looked very desolate. We landed in the flattest possible places just because that's the safest place to land. But we were really excited to see, I shouldn't say we, because this is before my time, the scientists who landed the Viking landers were very excited to see, initially they had this life experiment where they essentially added water and some food, and they saw what happened. And they got this huge release of oxygen and other gases. And so at first, that seemed like a robust, yes, there's life here, right? But as they looked at those data a little bit more carefully, they saw that the release was very fast, way too fast for microbes. Microbes get very excited when they get food and water, but they take a little time to actually digest that and produce signatures. And so the consensus now is that even though, there was a release, that was probably chemical. So that's abiologic as opposed to biologic. And that's probably because, as we've learned from later missions, there is actually something called perchlorate in the Martian soils. And so we like to think of this as probably rocket fuel is the name that you would call it if you were a non-scientist. But basically it's something that's very an oxidizing material that will react when you add water to it. And so that's probably what caused the Viking release. But that was something we didn't know when we sent that experiment.
Now I've heard of that perchlorate before. I've heard about this in the soil there. Is it all over Mars, or is it just, how much do we know about where it is?
It's hard to say, right? So in the landing sites where we've actually had instruments on the ground, we found that there is quite a bit of perchlorate in rocks and soils. Now, it's not actually uniformly distributed. So right now, in the Gale Crater Curiosity rover mission landing site, we're actually in a place where there aren't any perchlorates. But in a previous spot where we roved from, there were perchlorates. So they're everywhere, probably, but not homogeneously distributed.
Yeah, one reason I asked that is because, I was watching the movie The Martian a while back, and I remember the
Awesome.
perchlorates, and I was watching it and thinking, but wait a minute, what about the perchlorates? Would that kind of screw up this whole potato farming? I don't know.
I mean, you probably don't want to eat too much perchlorate.
I would guess so.
Yeah. Okay. Well, but it's possible he was in a spot where there wasn't a lot of perchlorate, so maybe it was possible.
Well, they did have a big rocket launch there, too, so the soils in that area, probably were contaminated with perchlorate anyway, even if they weren't there before.
Oh, that's right.
We'll let it slide.
Okay.
Have you seen The Martian?
Yeah, of course. And I read the
Did you
book.
read it?
I read the book too.
Yeah, I will say The Martian is one of those book/movie adaptations, whatever, that it tracked pretty closely, and I really genuinely enjoyed both.
Agreed. I really
Yeah.
liked it. I really liked The Martian.
I'm waiting for the trifecta where we send people to space the third time to get Matt Damon.
Yes. I also love Matt Damon, so that was fine too.
But we were not here to talk about The Martian. Larry did actually do he went asking questions
About real science that they're doing. Yes.
Now, what you guys are talking about now, this current work, it gets into the issue of biologic versus non-biological desert varnish. That's the focus, right? So first, can you explain what desert varnish? I call it desert varnish because it's rock varnish. I grew up calling it desert varnish. A lot of people don't know what this is. Can you explain what it is?
Sure. So rock varnish is this dark, shiny coating that you see in deserts all over the world. You probably stepped on it if you've been in a desert. You can see a rock, and it looks just really dark and shiny. And it turns out that is a material that is a mixture of clays and iron and manganese oxides. And what's so interesting about it and so intriguing is that it's the same all over the Earth. No matter what rocks it's on, it's always about the same composition. So it's really been this enduring mystery in geology. Now, what is this coating that is ubiquitous in these arid locations? And there are places where there are no available iron or manganese oxides to make that. Where is that material coming from? So it's something that has been an active area of study for at least 100 years, if not longer.
What do they look like?
Black. So I grew up in the West, and until about 10 years ago, I thought that was just the color of what I considered volcanic rock. But what it is a coating that forms over the surface of the rocks over hundreds, thousands, tens of thousands of years.
If you were to take one of these desert rocks, take a rock in the desert and break it in half if you can, you would see right away that the inside is a totally different color than the outside, sometimes dramatically so. You can see, the dark, shiny brown to black coating, which has all this manganese in it, doesn't go very deep at all. We're saying microns, right? So 10 to 30 microns, even 500 microns, that's half a millimeter. That's very, very thin. So you can immediately see that it's not what the whole rock is made out of if you break it in half.
And Native Americans have used this, right?
So rock varnish typically forms on surfaces that are not easily eroded because it takes so long to form. So it probably forms on softer rocks, but it gets washed away by chemical and physical erosion. So on harder rocks, it can actually build up. And so, and as I mentioned, it's oftentimes very different color than the inside of the rock. So this dark coating is much darker than the interior. And so Native Americans have actually used this as a canvas for art and communication. So you can see what are called petroglyphs carved into this varnish. So you'll see, a very dark surface with this lighter material uncovered in sometimes very intricate pieces of art on the rocks.
Do the petroglyphs have any scientific value in terms of studying the formation of varnish?
Maybe the other way around. So you can roughly get an idea of the date of the petroglyphs. If they have started to varnish over again, they're older. Not so much varnish if it's, just the color of the underlying rock. They're younger, say 300-400 years old.
So Larry, I will admit I don't think I've ever seen this rock varnish stuff.
Yeah, well, it's super common in desert areas, so I could probably walk outside and find some right here in New Mexico, in central New Mexico, but it's not common in other areas. It's literally, we can take a light colored rock, and if it's leave it out in the sun for hundreds of years, it'll develop this coating. And
so why? But so there's rocks everywhere, though. There's rocks here on the East Coast. Why is it so prevalent? Do you know why it's so prevalent? Out in the West and out in your neck of the woods?
Well, I think that's one of the things these scientists are trying to figure out, because I remember hearing about it as a high school student, and I first went on field trips to desert areas from California, and saw it. But even then, no one was sure how it's formed, and that's sort of where this science they're doing it's an Earth science as well as a Mars science thing, because I hope if they can figure out what's going on here, it might tell them something on Mars if they find similar kinds of layers on the surfaces of rocks.
Oh, well, that's pretty cool.
Nina was talking about where does the manganese and iron come from. There's plenty of iron in most of these rocks to form that glaze or varnish on the surface. However, the manganese, that's not the case. And it appears that a lot of the manganese and iron is coming from atmospheric deposition.
So that would be dust?
Dust, rainfall. And this occurs over hundreds and thousands of years. Our best guess. Now, does this varnish occur in little spurts and pauses, or is it a constant growth over time? That we don't know either. But the interesting part is if that manganese and iron is deposited onto the surface of these rocks, how does it get immobilized there? How does it go from manganese and iron that are soluble in water to an oxide form that forms this very tough crust on the surface of rocks? And that's where microbes might play a role.
this isn't exactly something you can duplicate in a lab, it sounds like, because it's such a long process, right?
And that's been one of the reasons we've got a 100-year question.
Many have tried, but it's also very hard to take microbes out of their natural environment and then make them, exhibit the same behaviors in the laboratory. And especially the microbial communities that we find on these rocks, which I'm sure Chris can tell you more about. These aren't very happy, right, in the lab.
Right. They grow very slowly, so they're adapted to conditions of low water, importantly, high irradiation, and that's one of the reasons we're interested in Mars and Varnish connection.
And so another part of the connection that we're trying to make is that, we're not really sure on Earth the origin of varnish. Is it a biological product or is it not? And so if it's not, we might expect that in any arid environment you would form varnish through these abiological processes. And so then the question is, on Mars, would we expect to see varnish or not? Many have predicted that we should see varnish because the surface of Mars is like the coldest, driest deserts on Earth, which do have rock varnish. So we haven't seen ubiquitous rock varnish on Mars yet, but we have seen some very intriguing signs that manganese is being concentrated on Mars rocks in some places. So this now leads to the question, okay, so what's the origin of varnish on Earth, first of all? Is life involved? And if so, does it leave behind signatures that we could see on Mars with our rover instruments?
I want to know, this is a very typical question, but how are they actually doing, how do they do this on Mars? How do they find these?
Chemcam.
What are you saying?
Chemcam.
CHEMCAM?
Correct.
Like a chemical camera?
I believe that's exactly what it stands for. Or chemistry and camera.
Ooh, chemistry. You should know something about that.
Ugh.
Chemcam is an instrument that is on the Curiosity rover, which is on Mars right now, operating in Gale Crater. Chemcam was built by Los Alamos National Laboratory, and it's also operated by us here in New Mexico. And it's actually two instruments in one. So Chemcam is short for chemistry and camera. So the chemistry part is a rock vaporizing laser that actually vaporizes a little bit of rock at a distance from the rover, so up to 23 feet away. And it creates this really bright light, and we can look at the light that's producing back on the rover, and we can see what elements are in that target. It's a really rapid technique. So every time we pulse our laser, we get another spectrum. So that's the chemistry part. And then we can put that chemistry into a geologic context by using our camera, which is a little remote micro imager that gives us a very small scale image of where we shot on the rock. So we can say, hey, we shot that little white grain or this little dark matrix, and we can see the chemistry differences with the laser information and then put that into the context by seeing where on the rock it is.
Could you explain how you get the chemistry from a laser?
Sure, yeah. Waving my hands here. So the technique that we're using on Chemcam is called laser-induced breakdown spectroscopy, or LIBS. And so the way that LIBS works is that it adds energy to the target, a lot of energy, right? We're vaporizing material. It's hotter than the surface of the sun in this little tiny spot, which is only about 0.5 millimeter in diameter, right? So it gets everything really hot, so everything breaks apart. You have no molecules, you just have atoms. And so as they kind of cool and come back into a solid state and lower energy levels, they will emit photons at characteristic wavelengths. So you can look at the color of light that comes out and say, this element is in this target.
You're zapping it, and you're also reading the light coming.
That's right. And so we have a telescope back on the rover, because this is a really small spot, right? I said 0.5 millimeter, so it depends on how far away you're shooting. It can be a little bit bigger, but not by much, right? So you're making a little burst of light, which you can actually see with your eyes. If you were standing on Mars next to the rover, you'd be able to see it. And so the rover can actually collect that light during the daylight, so there's all kinds of sunlight too, and then we can actually look at that light and say, okay, what does the spectrum look like? And you'll see that it's not a continuous spectrum, right? If it's continuous, you would have all wavelengths. But instead we see peaks at very specific places, and that's what tells us what the rock is made out of. We have an engineering model of the Chemcam instrument right here in our laboratory. So we can place samples in our Mars chamber, and get data that are equivalent to Mars. So we can say, okay, here's our rock varnish that we collected. What would it look like if we saw it on Mars? Because that's the thing. On Earth, we have all instrumentation available to us, and we can use the gold standard measurement techniques. On Mars, we're limited to what we bring with us, and sometimes you can't bring everything. And until we do sample return, we're limited to the few experiments that we send. So part of what we're trying to do here, we're trying to answer these two questions. One, what's the relationship between varnish and life, and what are those signatures in terrestrial laboratory techniques? But then how do we translate that knowledge to the more limited instrument suite that we have on a Mars rover? So we're lucky enough to have been selected to build another instrument for the upcoming Mars 2020 rover. And this instrument is going to be called Supercam because it's similar to Chemcam, but it has some super capabilities. And so the biggest difference is that, so we have the LIBS laser technique, but we're also going to have Raman spectroscopy. So this provides us with structure. So the LIBS technique gives us chemistry, and chemistry is awesome. But for a geologist, you need more than just chemistry. You need to know what are the elements, but you also need to know how are they arranged. That's mineralogy. So what Raman does is it provides that structure information. So it's a lower power laser. We don't vaporize things. We're just exciting the molecules, the bonds. So we're seeing what the bonds are. So we can use the LIBS to find out the chemistry and then use the Raman to find the mineralogy. And therefore, we can get a full picture of what these rocks are.
Supercam.
Supercam.
I know. But I think like Chemcam's more fun to say.
Chemcam, Supercam.
Chemcam.
When is this rover scheduled that this will go on?
Mars 2020 is going to launch in 2020.
Launch, okay, that's
Yeah.
pretty soon.
It's very soon. Terrifyingly soon, but we're going to be ready. We're going to do it. So we should launch, let's see if I can remember. We're going to launch in July of 2020 for a February 2021 arrival.
Have they chosen a landing site or anything that's going to be kind of feed into what you guys are doing at all? Do we know?
Yes, I have been quite involved in the landing site selection process, and essentially, the scientists get together over a series of yearly meetings to hash it out. Basically, say here are some sites, based on what we want to accomplish with the rover, then which sites can address those mission goals, and it can be very contentious, very exciting meetings, a lot of raised voices, but it's all for the good of science. And eventually, at one point, we had our final meeting in which we made our recommendation to NASA headquarters. And then NASA headquarters decided. But luckily for us, they went with our recommendation, and that is Jezero Crater. And so Jezero is a crater that is at its very surface seems very similar to Gale Crater, where we are with Curiosity. It is a middle-age crater, so that's, if you know your geologic timeframes on Earth, that's in Hesperian. So that's about 2 billion years old. That's pretty young for Mars, because there aren't very many young terrains on Mars. So this is a place that is a relatively young place that can contain some ancient bedrocks, but has a whole bunch of features on the inside that are much younger. And in particular, it looks like there is a delta deposit that was deposited into a long-standing lake. And that's very similar to Gale Crater, but the reason we're so excited to go here is because the mineralogy is totally different from orbit. So we can see that there are actually carbonates here. Carbonates have never been seen on Mars in situ. And so we've seen some really intriguing hints of carbonates from orbit, but we've never seen them on the ground. So this is going to be our first opportunity to see that. And carbonates are really interesting because on Earth, most carbonates are actually made by microbes, right? All the limestones you see are just the dead bodies of sea creatures from the past. On Mars, we might expect, okay, maybe it's not sea creatures, but we might expect there to be a lot more carbonate given that it has a carbon dioxide atmosphere. And if there was a lot more water in the past, where are those carbonates? We don't know. We don't really understand how they form. So this will give us our first glimpse of, what does that carbonate look like? And that will also help us ascertain if that is made by life or not made by life. But also this sort of lake environment is just a perfect environment for life. On Earth, an environment like that would be inhabited. On Mars, we don't know if it was, but this is a great place to look. And from Gale Crater, from our studies with Curiosity, we know that manganese is actually much more abundant on the Martian surface than we had previously thought. So I think this is going to be another place for us to test hypotheses about high manganese concentrations, such as rock varnish.
On Mars, where you guys are going to do this, when you zap the rocks, you're not leaving any mark on the rocks. I mean, you're not doing petroglyphs on Mars, are you?
In fact, we are leaving little marks on the rocks. So every time that we zap our laser, we actually ablate micrograms of material. So that's not very much, but we do multiple pulses in one location. So typically we'll do 30 to 150 little zaps, and that actually digs a little hole into the rock. So we are leaving little holes on rocks all over Mars. And in fact, we can see those images. We can see those in images. We can see the little holes where we did the analysis in our remote microimager images.
I have to ask, Nina, have you left your initials on Mars?
I cannot confirm. No, did I? No, I have never. Because it turns out it's really hard to move the mast. So our instrument is on the rover mast. And so it is really hard to come up with fine control for that mast. And we're actually limited by the gear size, right? So we have like specific motor positions. We can't go smaller than that. So we can do side to side and up and down, but it actually gets really hard if you want to try to do something that's diagonal. And so I am actually on engineering operations, so I have to make these spacecraft commands. And I, as much as I would love to write a big N on there, that would take forever. It'd be so annoying.
Sounds like you thought about it, though.
I'm not going to say I haven't thought about it. Right now, we limit ourselves to lines or like a box, a grid, because that's a lot easier.
I think I've seen some pictures from Curiosity showing a little line of holes. You could do Morse code.
We could if we just spaced them, and sometimes we accidentally do. We try to keep it even spacing, but because we're doing such a fine pointing, the wind can actually blow us off course a little bit, or thermal expansion or contraction. So in fact, sometimes our pointing is a little bit off. It's actually much more challenging than I anticipated, but that's field work, right?
I would love to have my initials in a rock on any planet, I guess.
Would that make you like space then? If you
you
had a personal imprint on.
Did you ever put your initials in cement or carve them in a tree or anything like that?
I was never that destructive of nature.
Concrete's not nature.
No, that's true.
All right. The thing I can remember is my dad, when I was in second grade or something, he got me a little pocket knife. I was in Cub Scouts. It was a big deal. You get a whittling chip. It's a thing. But he also got a Dremel, right when Dremels first came out.
I don't know what that is.
Oh, sorry. It's this little, it's like a tiny little drill that's very microfine. And so he literally initialed into this little stainless steel pocket knife
your name.
My name, and I still have it. It's hilarious. But every time I show him that, what were you doing? He's like, I don't know. I had a new toy. I thought it was kind of cool.
That's cute.
So not quite as impressive as lasers on Mars, but
yeah.
Shout out to my dad. All right, folks. Well, that's all from Third Pod from the Sun.
Thanks so much to Larry for bringing us this story, and to Nina and Chris for sharing their work with us.
This podcast was produced by Larry and mixed by Kayla Suri.
We'd love to hear your thoughts on our podcast. Please rate and review us. You can find new episodes on your favorite podcasting app or on thirdpodfromthesun.com.
Thanks all, and we'll see you next time.